Hi guys, we're team Medsonic, and let's start with our Senior Design Expo presentation. Let's start with some introductions.
Can I just stop real quick? Is James supposed to be in the meeting as well? I don't think so.
I'm not sure.
I'm just going to admit for now, and then we'll see. Sorry, continue, please.
I'm Ambrina Abbasi. I am the PCB and financial lead.
I'm Ebenezer Argyle. I'm the software or embedded software lead.
Eric Dahl. I handle the signal processing, and I was also the communication liaison between us and our sponsors at Medsonic.
And I'm Selassie Etchi. I serve as team lead and also power lead.
My name's Andy. I do software in Python.
My name is Jabin. I'm responsible both for MATLAB and LT-SPICE simulation and assist on software development.
And we are Medsonic. This year, our project was the ultrasonic transducer test platform. We teamed up with Medtronic, who have this ultrasonic transducer tool called the Sonicision product that is meant to be a surgical tool for minimally invasive surgeries. The tool uses longitudinal ultrasonic vibrations produced by the piezo-driven transducer in order to simultaneously cut tissue and cauterize blood vessels. Our job was to expand and modify the previous team's Nexonic's test platform for this tool. In the body, we have different types of tissues with different impedances, and the previous team was only able to implement an open loop feedback algorithm in which the user had to manually program for that specific impedance. We were tasked with making changes that would allow for easy, user-friendly, and autonomous operation. Different load impedances attached to the transducer shift our system off of resonance, meaning that we aren't able to output 100% power. So the goal of our loops is to lock down our system in velocity and frequency so that we can deliver efficient power at various set points. Our team this year fabricated two boards, a variable buck and a Class B amplifier. We modified the Python GUI as well as closed the previously open feedback loop for autonomous operation. Our variable buck acts as a power supply for our Class B amplifier, which is responsible for taking inputs from both the velocity and frequency control loops and outputting an appropriate velocity scaled and phase locked sine output wave that will drive the transducer. Our Python GUI allows us to peak and prod at the open and closed loop system intervals.
So when we first began this project, we were under the impression that all of the heavy lifting would be done by the primary processor. And by that, I mean, we thought that the computation heavy algorithms that we knew that we would have to be doing, the signal processing that was going to be involved in this project, we thought that would occur during the main program. We realized this wasn't realistic though, a couple weeks into the project, and we learned more about what this would entail. So we started researching other solutions. How else could we approach this problem? And one of the things that we learned in our research was something called a dedicated digital signal processing chip. And the primary function of these are, it can do transformations, it can do correlation, and it's just like one line of code. So they're really easy. But it was, as we learned more about our project, we learned that this was kind of overkill. Our project was transforming a pure sinusoidal wave, which only has components at the resonant frequency. So we didn't really need to use a chip that would compute the entire transformation. Rather, we could evaluate the transformation at the resonant frequency, and that would be enough. Now, while the main processor still wasn't really able to handle this while doing everything else, doing the interrupts, poking and prodding the sensors. So we started learning about the control law accelerator, and I'll hand it over to Andy at this point.
Yeah, so I'm going to continue talking a little bit about changes to our initial design.
Andy?
Can you guys hear me?
Yep.
Yeah, I'm going to just continue talking about changes to our initial design and how we actually implemented those designs and what actually resulted at the end of the semester. So like Eric said, we initially researched into adding some additional hardware onto our motherboard, this DSP chip that would allow us to calculate phase and magnitude super easily. And let me go really briefly into why we need to calculate phase and magnitude. So in order to deliver real power to the transducer, we need to have voltage and current in the same phase. And because these are sinusoidal waveforms, when they're in phase, they're going to deliver the maximum power to the transducer. And so in order to do that, we need to calculate the phase of those signals at any given time. And so that's why we thought about this DSP chip in the first place. But like Eric said, due to our hardware constraints and due to specifications by Medsonic, we decided to use the two processors that are currently on board. And that is the main C28X core, which is made by TI, and a coprocessor called the CLA that sits right next to it. And so the way that works, instead of having a DSP chip do all the lifting for us, we have the CLA calculate real and imaginary sums over 12 points in a single cycle. And after calculating the real and imaginary terms, we sum this up, and this allows us to get our phase and magnitude calculations. And this is a nifty little trick that was taught to us by Keith and Medsonic called a correlation sum. And once we have these real and imaginary sums, we can pass this back to our C28X, which has trig functions that really easily let us calculate phase and magnitude. And since we have these calculations, it's really easy to eventually close the frequency loop.
So during the duration of our project, we've ran into several compromises and troubles that we've had to overcome or decide upon, and we'll discuss that right now. One of the compromises we made a little bit later in our design choice was allowing the buck to stay at a static voltage rather than varying with the sound amplitude. This was so essentially our Class B amplifier, which drives our transducer, requires two inputs: a sine wave that will be amplified, that will be used for the transducer, and also a voltage rail for the sine wave, provided via our buck converter. And pretty much allowing the buck converter to stay at this high rail would mean that our system would be less energy efficient, but overall it just reduced the complexity of the project for us to complete this on time as well. Another trouble we went through was accidentally flashing our board with code that didn't allow us to reprogram our board again. This was because we had initially switched it to our synthesizer clock, which is our external clock, at the beginning of our operation. And whenever that happens, there was just some communication error with our debugger and our board. And for a little bit, we had a board that was bricked, and we had to hard reset our flash to get rid of that memory or that code.
Yeah, and I'm going to talk about a couple other troubles that we ran into. It was hinted at before, but we actually ran into some complications when it came to being able to calculate magnitude and phase at a 56 kilohertz tone, which is the resonant frequency of the transducer unit that we based our system off of. So a lot of our phase calculations, in order to stay in frequency lock, our phase calculations have to be very frequent and accurate. And so these calculations take a lot of compute time because they're based off of trig functions on the processor. And so in order to cut down on how much work the processor was doing, we employed the use of the CLA, the control law accelerator, to offload some of those phase calculations almost in parallel, so that we could keep our sine wave, our 12-point sine wave, operating at 56 kilohertz, and also be able to accurately dictate magnitude and phase. One of the things that we also ran into were serial communication issues due to our baud rate slipping. One of the facets of our system was the ability to peak and prod and change system dynamics through the use of Python GUI that we helped develop. And so what happens is we're using a frequency synthesizer, the chip on the motherboard, as the clock for not only running a lot of the system parameters, but the motherboard processor clock gets replaced with that frequency synthesizer clock. So when that moves around, the entire motherboard CPU frequency moves around. And so with that, our baud calculations are off, and we're not able to sustain an even baud rate between our host computer that runs the Python GUI and the processor side. So we compromised that situation by frequently updating the baud calculations and frequently reconfiguring the baud rate of the system so that we can achieve communication despite frequency changes that we needed to make to stay on, to keep the system on resonance. And with that, I'll lead into Ivan, who's going to talk about how COVID changed the dynamic of our project.
So as we know, the whole situation of COVID is very unexpected and has a very high impact on our academic learning, especially for our capstone class. And there are definitely a lot of challenges that we face together in this situation. One of the biggest issue is that we are prohibited to work together in person, and this makes it a lot harder for us to communicate with each other. Another issue that we are facing is the lack of equipment in general. For example, we don't have access to high voltage power supplies as we wanted to, so that we couldn't draw as much power as we wanted. This is something we wish we could have, and also lack of the equipment amongst the team. We spread out the entire development process. We managed this by talking to our sponsor and scheduling Zoom meeting to work with each other. And just based on the progress we made, we actually think that we overcome this challenge and adapt the situation very well.
Cool. So now we'll talk about our system as a whole and how the operation of it works, as well as what we accomplished during our time. And we'll have demo videos to show what we've done. So if you can look at our system design in our middle of our board, you'll see that there are 2 inputs into our system, and one of them is to a wall adapter that will supply a 12-volt DC input, as well. That will power our board and other modules of our board, and as well as a user or an actor that will give in user commands and activation and just other commands to for the operation of our system to our command manager. And our command manager really is our central unit that pretty much puts everything together, takes in different command inputs and everything, and outputs a lot to pretty much set this whole loop of operation. And our command manager really is our MCU. And if you'll see that some of the user commands that could be sent would be either allowing operation during closed loop or operations during open loop. And during open loop, the user is able to change synthesizer frequencies from our GUI, as well as the amplitude of our sine wave. They can select different max amplitudes and different set points for our velocity to our velocity lock to loop around, and it just has a lot of functionalities for the user to be able to play around with. The next thing we will talk about is our velocity manager. And our velocity manager has 2 separate parts, and it has one of them is with our buck output, which will be fed into our Class B amplifier as our voltage rail for our sine signal that's fed into the Class B amplifier and later amplified. And what we'll see right here is a video of a demo of our buck amplifier or our buck converter being able to change its output with a PWM signal that we send, varying the duty cycle. So Selassie, if you could play that.
And I'll start playing this video right now.
We can't hear your sound, Selassie.
My bad. What'd you say?
We couldn't hear the video.
Yeah, my bad. There's no real way around that. I hope.
You can share the audio if you go to view options or I guess share options in the top bar of the when you're sharing.
Share options.
And there should be an option that says share computer audio somewhere in there.
Yeah. All right, can you guys hear this now? And so the variable buck has 3 inputs. One of them is this 12-volt rail, which gets sourced from the motherboard and goes to the input pins right here. And you can see these 2 wires are input pins from the motherboard, which represent the high side and low side PWM out inputs that regulate the output voltage of the buck converter. So if we take a look at this oscilloscope screen, you'll see 3 different waveforms. In yellow, we have the input to the buck, which is sitting at around 12 volts. And in purple, we have the output of the buck, which is sitting at 6 volts. And in blue, we have the high side input PWM to the buck converter, which is sitting at about 50% duty cycle. And so what happens is that that output magenta waveform is 50% of our input 12 volt waveform. And so in order to regulate the system, we have some open loop controls set up by the Python GUI. And so we can increase and decrease the duty cycle, and every single button press will increase or decrease the duty cycle by 5%. So we can see that if I increase the duty cycle via the buttons, you'll see our purple waveform, which is the output of the buck converter, go up, while the blue waveform, which is the PWM, increases in duty cycle. If I go down in duty cycle, you can see the same linear trend. Okay.
Cool. So another point for our velocity manager will be our sine amplitude that is fed into the Class B amplifier, and we are able to vary our amplitude in 2 different modes of operation. So in open loop operation, the sine amplitude is varied with our user inputs, and we could just scale that up or down using the GUI and specific buttons, and we'll show that in our demo as well. Another thing that another one that we'll show is under closed loop our operation, and this would be to regulate around 2 specified set points from our velocity PI loop that will pretty much regulate power at that specific velocity, and Slossie will show that video as well. And this video will show just the open loop operation, and then later in our velocity lock video we'll show that it works under closed loop as well.
Here's our motherboard with a probe connected to our DAC8 output, which is outputting a 12-point discrete sine wave that it was used to drive our Class B amplifier, as well as used for our phase and magnitude calculations. What you see now is a 3.3 volt peak-to-peak waveform, and we can now go into our GUI to change that or increase and decrease the sine wave by pressing a few buttons. So decreasing each time by 300 millivolts. Now we'll increase it back all the way. And now we're going to change our max limit to 2 volts. And we'll see that it's decreased to 2 volts and cannot increase anything past that, although buttons are being pressed.
Okay. All right, so now I kind of want to talk. Can you guys hear me?
Yeah.
Okay, so now I kind of want to talk about a little bit more about what we accomplished when it comes to closing the loops, which is one of the requirements that we've had since the beginning of the project. So one of the things that we mentioned before is that in order to output entirely real power, we want our voltage and current waveforms to be in phase at all times. And so we need to take phase measurements and feed those into a software PI loop, which dictates in which direction we want to move our frequency synthesizer in order so that we can maintain phase lock. And we do that by using a correlation sum to calculate the magnitude and phase of our signals and effectively use that to dictate where we shift our frequency. And I'll show that demo video right now.
So over here we have our whole system set up. We have our motherboard connected to our Class B amplifier and the buck converter. And hooked up to this whole system, we have our ultrasonic transducer. And this is the actual blade that's going to be doing the cutting and the cauterizing. And hooked up to our buck converter, we have a DC power supply set to 20 volts and current limited at 1 amp. Now when we move to the scope over here, we're going to see 4 waveforms that are pretty important to us. The top purple one being voltage applied at the transducer. The green one is the current going to the transducer. The yellow is our sine drive DAC that goes into the Class B amplifier. And the blue is our IMFB, motional feedback. And so now we're going to send a command to the motherboard to change clock sources to the synthesizer. And so we're going to send it. And we see that the frequency has slightly changed to an external clock source. Now we're going to type in a command to close the frequency loop. And ideally, we should be able to see that blue wave phase lock to that yellow wave. And we can see, now that the control loop is on, we are phase locked to those 2 signals.
Okay, and to segue with that, now that we have achieved our goal of being able to put the system into frequency lock, meaning that we're always at a 0 phase angle, we're always able to output 100% real power to the transducer. Now we want to be able to dictate how much power we supply to the transducer. And we do that through the use of our velocity loop, which takes magnitude calculations into effect. And we essentially regulate our system to 2 different energy mode set points, depending on how much power that we want to supply to the transducer. And I'll show that velocity lock video right now.
So what we have here is our motherboard connected to our Class B and buck. We have some signals on our oscilloscope. The green one is going to be our sine DAC output that's outputted from our motherboard into our Class B amplifier that is driving the Class B amplifier and driving our transducer. The light blue one we see on the bottom is the motional feedback current, and the green one is the current to the transducer, and the magenta one at the top is the voltage in the transducer, so V-trans. Right now we are in phase and we have velocity locked, and we're going to see the 2 different energy modes or set points that we have set. So when we click it now, we go to 90 milliamps RMS, and we do this through a button, a 2-phase button that we have on the motherboard. This is our lower energy mode, and we increase it by pressing it to our higher energy mode, which is 130 milliamp RMS value.
So with both frequency and velocity loops closed, now we just have a little demo burning some tissue just to show you guys what we see on the transducer.
Yep. Okay.
So not a big burn because we weren't applying too much power, but that just goes to show kind of how our system works. And with that, I'll segue into Ivan, who will talk about what we learned.
Yeah, so throughout the entire years of capstone experience, we have gained a lot of things from this class. One of the most important things we learned is to work together as a team and focus on the same goal to deliver our project at a limited amount of time. And we also learned the process of developing the professional engineering products and the documentation that's needed to support the product. Another thing we learned is to balance the prioritize and skill task. Capstone is not a light class, and we have to learn to balance other courses and the capstone. This requires strong communication in team. Sometimes some of the team members have exams or projects coming up. We have to communicate with each other about the situation early so that others can know and make adjustment on this. Leveraging class expectation and our sponsors' expectations and other things that we learn in class. So For example, there are so many documentations that we need to finish for capstone, and this require us to know. I mean, this is good for us because we can know the design process and the materials documentation. But this process normally takes a lot of times in class. And also as well as our sponsor Keith also want us to make progress to make sure that the project is on time, that it's keep on track on the schedule. Therefore, we have to spend more time to work on both so that we can ensure that we can reach both the class and our sponsors' expectations.
Okay, and with that, I just want to give some acknowledgements. First, I want to thank the instructor team, so Andrew Femwright, Prayer, our TA, as well as the other TAs, and Leland, who have helped us a lot through the semester or the year as a whole. I also want to thank Keith Malang and James Schisler and Jake Johnson, the team at Medtronic, who have helped us develop a lot in our technical skills and also grow as people. You know, we spent a whole year on this project team together, and we've learned a lot, not only technically, but the social aspects of engineering and just life skills in general. And we've all grown from it. And I just want to tell you from the bottom of our hearts that we all want to say thank you for that, and that we really appreciate the time and effort that you put into investing in us.
Thank you, Keith.
And
Nice job, guys. Since we're a little tight on time, I'm going to open up. If anyone at Medtronic has questions, we'll take those because those are, I think, important ones.
How'd we do, Keith?
You guys did great. Can you guys hear me?
Yep.
Yeah. I mean, I'm when I think about where we started from, and I had some hard constraints for you guys. I had forced the Piccolo 0049, and that was something that I was putting you as part of our Medtronic ultrasonic next generation team. The work, the constraints that we had, and growing you guys through the year on ultrasonic basics, power basics, signal processing basics. I'm ecstatic. I mean, I'm just so happy with the way it turned out. There's always going to be a little give and take, couple lumps and bumps, as you go along, but you guys grew tremendously right in front of my eyes, and I hope you guys see that. There's not much I can really say other than I'm so very, very, very proud, and you guys, hopefully all the stuff that you learned, you'll carry into your careers.
Thank you.
Yeah. Any other last Medtronic comments? Just because I want to make sure we finish our 30-minute window, and I know Medtronic has other obligations for work.
Nope.
All righty. I guess I'm just going to leave with one comment that I think you guys haven't touched on. Like, documentation is what makes someone an engineer, as annoying as that is. Like, documenting how to do something. I think because you guys picked up the project from last year, so you guys had like all the documentation and you could see where it was good and bad. And that's like, unfortunately, like you guys are talking about how there's so much documentation. That's like what makes an engineer. That's part of it. So it sounds like you guys definitely kind of figured that out and learned a lot. So Sam, do you have any last comments?
Yeah, I think you guys did a really good job taking a pretty complicated problem and solution, just in terms of what it actually does and what it's trying to solve. I think you explained that very well, especially something like, the phase concepts, because those definitely aren't easy to understand and even maybe harder to teach. So I, as someone who was not like directly involved in the Medsonic project or your direct instructor, like I understood what was going on. So good job with that throughout the AT tests and final demonstration.
Thank you.
Yeah. I guess any last comments and we can let the team go. All righty. Sounds like we're all good. Thanks, guys. Awesome presentation. I hope you guys had fun this year. And yeah, good luck with wherever you end up going.
Thank you.
You guys.
Have a good day.
You as well.